Okay, let's do this problem from the book to see how we can use the safety factors for bolted joints and tension. So for a bolted assembly with 8 bolts, the stiffness of each bolt is given here, and the stiffness of the members within the grip is given there. The bolts are preloaded to 75% of the proof strength, so that's consistent with a non-permanent connection. Assume the external load is equally distributed to all the bolts. That's helpful. So whatever our load is, we just need to divide by the number of bolts to get the load per bolt. The bolts are M6 by 1s, class 5.8, so that's going to give us the proof strength, and this is going to give us the size, so we can calculate the proof load, and that will allow us to figure out what the preload is. A fluctuating external load is applied to the external joint with Pmax equals 60 kilonewtons, Pmin is 20 kilonewtons. Now, we're not going to do the fatigue part of this problem, so we can ignore the fluctuating part, and we'll just say, let's just talk about the external load is P is equal to 60 kilonewtons and solve the problem this way. So determine the yielding factor of safety. The way that the yielding factor of safety defined, it's a simple factor of safety. How much could you increase the stress on the bolt before it yields? So we're talking about how many times N could you increase, we'll call it N sub Y for yield. The stress on the bolt, we've got a normal stress on the bolt because it's being pulled in tension. It's kind of the stress in a cylinder with cross-sectional area A. How many times could we increase that before we yield, before we reach the yield strength of the bolt? Actually, even though we call it yield, the way this is typically defined is actually, because it's a bolt we talk about the proof strength. It's a little bit lower than the yield strength, sometimes a lot lower. It's whatever stress, the level of stress at which you observe any permanent deformation. It's not, SY is with the 0.2% offset method. SP is any observable permanent deformation. So at Shigley, it's labeled N sub P, but I'm going to label it N sub Y. Reminds us we call it the yield factor of safety, but it's really the factor of safety with respect to the proof strength. Okay, so what is sigma in this case? Sigma is the total load in the bolt, F in the bolt, the tension in the bolt, the resultant bolt load, the book calls it, divided by the tensile stress area, A sub T. Okay, FB is equal to the tension in the bolt, the resultant bolt load, is whatever the initial preload is, Fi, that's why it's I for initial, it's the preload, plus C, the joint stiffness constant, times P, the applied load per bolt. So Ny from this first one here tells us that is equal to SP, the proof strength, over the stress. But the stress, we can substitute in. We find that the stress is FB over AT. I'm going to go ahead and make this substitute. Well, okay, I'll write it out, FB over AT. That allows us to put the AT on top, right? Because we're going to divide, the bottom gets divided by AT. So really this on top, just recognize this. This is the proof load of the bolt. F sub P, excuse me, proof load. F sub B is the total tension in the bolt or the resultant load in the bolt. We get this here. Okay, so now I think that we can figure things out. Let's figure out what the preload should be. Fi is 75% of the proof strength. Okay, let's figure out what the proof strength is. Proof strength is SPAT. We're going to need that in a second. Proof strength of class 5.8. ISO 5.8, minimum proof strength is 380 megapascals. 380 megapascals times AT, the tensile stress area. We've got a M6 by 1 bolt. So M6 by 1 tensile stress area is 20.1 millimeters squared. And a nice thing is that a megapascal is a newton per millimeter squared. So we can just multiply these two things together and we're going to get something in newtons. We find 7638 newtons. So 75% of that is 5728.5. So that's our Fi. Our C in this case, C is the joint stiffness constant. It's given by Kb, the stiffness of the bolt, over Kb plus Km. And that is 1 over 1 plus 2.6, 0.2778. And P is the external load per bolt. We have a total load, P max, that's our total load. P total is 60 kilonewtons. So the load per bolt is P is equal to P total. We assume that it's divided evenly, divided by the number of bolts. So 60 kilonewtons, I think we have 8 bolts. 8 bolts, 7,500 newtons per bolt. All right, we've got everything we need. We can calculate what FB is, or what this thing on the bottom is. So this is what you find in the book. By the way, this equation appears in the book, and I showed how we got there. I'm just going to solve for what FB is. FB is a preload, 5728.5. Let's make it more clear that that's an 8. Plus 0.2778 times P, 7,500 newtons, is 7811.83 newtons. And so what we have here, FP on top, 7638 divided by 7811, 0.9777. Let's say 0.978. All right, that's part A. I think we'll get to reuse some of our calculations. So the next one will be a little bit shorter. So we already know that the yield factor of safety doesn't look so good, but that's why that we usually use an overload factor, because sometimes that number is very close to 1 and it's not very meaningful. Because theoretically, right, you have control over the preload. This is kind of saying the preload and the externally applied load could both go up by a certain amount, because the stress was determined by both the preload and the external load. But we've got control over the preload. So the overload factor, or the factor of safety with respect to overload, N sub L, that's how many times could we increase just the applied load without yielding. So we need to look at it from a little bit different perspective. We need to say, at yield, sigma is equal to Sy. And we saw before that sigma was Fi plus C times the applied load P divided by A sub T, tensile stress area, is equal to Sy. All right, let's move this over here. So this is another statement. This is the tension of the bolt equals the proof load at yield. The overload factor, N sub L, says how many times could we increase just P? We're not going to increase Fi by an amount. You know, if we wanted to derive the factor of safety on yield, then we'd put the N sub Y over this, right? That's how we effectively got the yield factor of safety above. Now we're saying we're just going to increase the applied external load P, and we're going to solve for what N sub L is. So N sub L is Sy AT minus the preload in the bolt. So this is kind of like the proof load minus the preload. How much tension in addition to the preload can you support in the bolt? Divided by Cp. So this is our formula. Let's go ahead and find this. So our proof load in the bolt, we got that product before, SYAT, was 7638 newtons, minus Fi, our preload was 5728.5, divided by 7500 times 0.2778. It's written in the opposite order. We get 0.91656. Okay, so this is the formula that's in the book. We showed where it came from. It comes from the assumption that we're increasing just the applied load. How many times can we increase the applied load per bolt before we yield? And we have a 0.91 overload factor of safety. So that's the more meaningful one, because theoretically we have control over the preload, so we don't often use this for design. This shows us that we can't even support the applied load. All right, the final one is determine the factor of safety based on joint separation. Joint separation occurs when the bolt extends enough, the members are no longer being clamped together, so the force between the two members, which is F sub m, goes to 0. But the force between the members is, well, the negative preload, this is in the book, plus 1 minus c times the applied load. That is pressure inside the members under a preload and applied load. And when that goes to 0, your joint gaps. That's when the parts begin to separate. So this gapping factor of safety says how many times could we increase P before this occurs? So what we're going to do is we're going to shove an n inside there, negative Fi plus 1 minus c times np. How many times can we increase P before this occurs, before we gap? So we solve, we have n, we bring the Fi on the right, we're going to divide by 1 minus c times P. They call it n sub naught, the gapping factor of safety. Yep, and that's in the book too. All right, let's figure out what it is. The preload was 5728.5 divided by 1 minus 0.2778 times the applied load per bolt, 7,500. We get 1.0576. So we are okay, barely, with respect to gapping. Our joint's not going to gap, but we will yield the bolt first. Now, if these were in the opposite order, right, if this was below 1 and this was greater than 1, then that means we're going to gap before the bolt yields. And that's also bad. We're not holding the joint together, so you need both of these to be greater than 1 in order for your joint to be safe. You'd prefer that they be much greater than 1, right? So you've got a factor of safety that's substantial. At what external load will the joint fail? We'll do that part. Well, the joint's going to fail whenever one of these two conditions happens, whenever we overload or whenever we gap. You know, it will fail at our factor of safety, n, whichever is the smaller of the two. I guess I'll write it out. The minimum of n sub naught and n sub L times P. And if it fails at n sub naught times P, if n sub naught is lower, then it's going to fail due to gapping. If n sub L is lower, it's going to fail due to the proof strength being exceeded. In this case, we have 0.91656 times P 7,500. The joint's going to fail when we apply 6874.2 pounds force, or newtons. I think we're in newtons. And you could confirm that the tension of the bolt, like let's just check this, right? The tension of the bolt, FB, is the preload plus C times the applied load, which is this in this case. So we've got a preload of 5728.5 plus 0.2778 times P, and we get 7638. Well, this is equal to the proof load of the bolt, right? So it's going to yield at that applied load. Now, the next two parts, I'm not going to do right now. I'm going to stop the video beforehand, but I want you to think about them. So I'll go ahead and read the questions and talk about it a little bit. Suppose the installation instructions were to torque the bolt to 6.9 Newton meters, and that was derived assuming that the bolts would be galvanized and they'd be clean, and so that was going to be, under that condition, the friction would be such that that would produce the desired preload in the bolt. That would produce the 75% of the proof strength preload. However, the bolts arrived from the supplier and they were greased for extra corrosion resistance. They wanted to make sure that they, during shipping, if they were exposed to something, they wanted to arrive in pristine condition, albeit a little bit dirty, and they weren't cleaned prior to being installed. So they were lubricated prior to being installed, and they were still torqued to 6.9 Newton meters. So in that case, at what external load will the joint fail? Think about that one. And the second one was ignoring this part E, right? So let's say that we cleaned the bolts off and the preload, we get exactly the preload we want. And your boss says, after you've realized in part D that the joint is actually going to fail at a load 6874.2, which is lower than the applied load of 7500, or what load could be applied. After you realize that the joint's going to fail, your boss asks you to fix the problem. So how do you recommend doing that? So there's lots of ways. You could redesign the joint using different bolts, etc. So think about the different ways that you could solve this problem, and think about whether there are clever ways. Especially, wouldn't it be nice if you didn't have to change the bolts? So think about what you could change with minimal changes to the design. The easiest way to solve the problem and get an effective factor of safety that's greater than 1.